Good morning friends, today we are going to discuss about the constant of simple harmonic motion. Already we discussed how we represent the simple harmonic motion by mathematical function. We discussed about that it is represented by either cosine function or the sine function or linear combination of cosine and sine function. Right? And also we discussed about that at the different position of a particle performing the simple harmonic motion, what about its amplitude or the displacement and velocity? With help of a figure, we discuss about this. Now, the displacement of a particle performing a simple harmonic motion is represented by the mathematical periodic function is xt is equal to a cos omega t plus phi, or xt is equal to a sin omega t plus phi. But generally, we represent this displacement as the cosine function because we start our oscillation of simple harmonic motion from the one extreme point on any side of maximum point. Therefore, the displacement of a particle performing a simple harmonic motion at time t is represented by this equation xt is equal to a cos omega t plus phi. Right? Okay. Now, how we do the graph of displacement versus time? So there is the cosine function, therefore graph is like this way. At time t is equal to 0 and phi is equal to 0, it starts from this. So here the time t and x position. That is only for understanding the graph of displacement versus time. Okay. Here the a, omega and phi are the constant of simple harmonic motion. And they determine the characteristic of simple harmonic motion. That means by knowing the value of a, omega and phi, we can say about how the particle performs the simple harmonic motion. That means the characteristic of simple harmonic motion is obtained by knowing the value of a, omega and phi. Okay. Now, here the terminology is that xt is the displacement at any instant time t. A is the amplitude. A is known as amplitude of the oscillation. Omega is angular frequency, and this bracket omega t plus phi, that is known as the phase of motion. And this phi is known as the phase angle or the phase constant. Today we are going to explain this parameter a, omega, omega t plus phi, and also the phi. For that purpose, what is the definition of amplitude? Definition of amplitude is that the magnitude of maximum displacement of a particle performing the simple harmonic motion. Here, already we know that the simple pendulum is perform the simple harmonic motion like this. At any instant of time, what is the maximum displacement from the mean position? That is known as the amplitude. This point is x is equal to 0, that is x is equal to plus a, and this point is x is equal to minus a. So maximum displacement is in this side. From mean position is a. Therefore, a is amplitude. That means the magnitude of maximum displacement of a particle. That is known as the amplitude. Now, the easy definition of amplitude is that the maximum displacement of oscillator on either side of mean position. Here, in this side, the maximum displacement is this. On this side, the maximum displacement is this. So maximum displacement in either side of mean position, that is known as the amplitude, that is denoted by here positive and negative sign shows the direction. But the magnitude of amplitude on both sides are same. So A also this side A, that is on right hand side, that is on left hand side. Because the displacement is a vector quantity, so to represent the displacement as a vector, the sign is required, therefore positive and negative value. Okay. The SI unit of amplitude is the meter, because that is measured in length, therefore SI unit is meter, and dimensional formula is only the length unit is measured, therefore the kg is 0, time is 0, therefore M0, L0, L1, T0. Again, the dimensional formula of amplitude is M0, L1, T0. Clear is? Okay. The displacement of simple harmonic oscillator changes between extreme points plus A and minus A. So continuously displacement changes with time. So displacement of particle depends on the position at that instant of time of a particle. Therefore, the displacement of the particle performing simple harmonic motion changes between extreme points plus A and minus A. The graph of displacement as a function of time, or the displacement versus time, with phi is equal to 0 for different amplitude is shown in figure. For that purpose, we are doing a graph of amplitude versus time for two different values of amplitude. For that purpose, the graph 1, having the amplitude is 1, that is the y is equal to 0. So that is the displacement, that means the displacement on upper side of a mean position, and that is the displacement in lower side of a mean position. So here x is equal to 0, the y is equal to 0, that is the y is equal to plus E. So the graph of displacement or the amplitude versus time is shown in this figure. Here the amplitude of this graph is A. The curve A1 has the amplitude is capital A. Now the second graph, having the phase phi is equal to 0, therefore the displacement is supposed to be. Therefore y is equal to b is the maximum displacement. The graph is shown like this manner. Both graph which is at the maximum value at the same time and which is at the mean position at the same interval of time, because the frequency are same, periodic time are same, but the amplitude are different. Here the one simple pendulum is oscillates between plus A and minus A. Now the second simple pendulum is oscillates between the plus B and minus B. So both represent the simple harmonic motion, and the amplitude or the displacement versus time graph is shown in the figure. Okay. Now what is the phase constant phi? Before discussing our phase constant about phi, what is the omega t plus phi in equation? Equation of the simple harmonic motion is x is equal to a cos omega t plus phi. Therefore, the position of a particle is determined by the equation xt is equal to a cos omega t plus phi. A is amplitude, omega is the angular frequency, and this bracket omega t plus phi is known as the phase of the motion. Is known as the phase of motion, which shows the position of motion of oscillator at that time. Now, there is the phase of motion, that means by substituting the different value of t in this equation, that represents the position of a particle at that instant of time. Therefore, that is known as the phase of motion. As we substitute t is equal to 0 in this equation, so what's happened? Only we obtain the phi. This phi represents the phase constant. That means that is the initial position of a particle which performs the simple harmonic motion. Clear this? So this way, here the amplitude and phase constant, and we also going to discuss about the phase of a motion and phase constant. And then we are going to discuss about the periodic time and angular frequency, and to obtain the relation between the periodic time and angular frequency. Now listen, after the omega t plus phi is the phase of motion. Now, we are going to discuss about the phase constant or the phase angle or the initial phase. Initial phase of motion. For that purpose, at time t is equal to 0, the phase of simple harmonic oscillator is known as initial phase or the phase constant or the phase angle. Already we discussed about the omega t plus phi. Omega t plus phi is known as the phase of motion. Phase of motion. If we substitute t is equal to 0 in this equation, so this term becomes 0. So phi is obtained. This phi is known as the initial phase or the phase constant or the phase angle. Actually, that represents what is the initial position of a simple harmonic oscillator which performs the simple harmonic motion. On the base of the initial phase phi, we judge about that the initial position of a particle which performing the simple harmonic motion. If the amplitude is A, then at time t is equal to 0, the initial phase phi can be determined from displacement of a particle. Displacement is this: xt is equal to a cos omega t plus phi. That means that is the mathematical representation of displacement of a particle performing a simple harmonic motion. Already we discussed this equation. xt is equal to a cos omega t plus phi. Our aim is to obtain the equation of initial phase or the phase constant phi. We substitute the t is equal to 0 in this equation. Therefore, xt is equal to a cos omega t plus phi. Here the amplitude of oscillation, that means the maximum displacement of a particle is A. Therefore, xt is equal to a cos, that becomes the 0, because we substituting the t is equal to 0 only the cos phi. Therefore, xt is equal to a cos phi, therefore cos phi is equal to xt upon a. xt is the displacement of a particle at that instant of time, and a is the maximum displacement. Therefore, phi is equal to cos inverse xt upon a. So thus we can find out the initial phase of a particle which performs the simple harmonic motion, or we can also find out the initial position. The graph of displacement versus time for different phase and for same amplitude. That means here we consider the two particles perform the simple harmonic motion with the amplitude are same, but the phase are different. At that time, what should be the shape of graph of displacement versus time? So here in figure, so yellow line represents the graph 3, having the amplitude is A and phase is 0. So at time t is equal to 0, the particle which perform the simple harmonic motion with the amplitude A and phase 0. So at time t is equal to 0, that is an extreme point. That is an extreme point. Yes, we do the graph of this. That means the particle performing the simple harmonic motion, x is equal to 0. For graph 3, the initial position of a particle is at here, x is equal to plus a position. Clear? Okay. Now, our fourth graph represents the simple harmonic motion with the amplitude is same, but the initial phase is minus pi by 4. Minus pi by 4. That means this particle also performs the simple harmonic motion on the same path. That is the x is equal to 0, that is the x is equal to plus a. But the initial phase is minus pi by 4. So this particle is at time t is equal to 0 at this position, till node reaches at the extreme point. So there is the position at time t is equal to 0. Again, here the graph of displacement versus time. 4. Two particles performing the simple harmonic motion with the same amplitude but different initial phase. Here the yellow line, that means the graph 3, has the initial phase is 0, amplitude is A. So the graph is this way. Regular graph. Now, how it performs the simple harmonic motion on a linear path? So here, there is the mean position, there is x is equal to plus a position, and there is x is equal to minus a position. This graph represents at time t is equal to 0, the particle is at extreme point x is equal to plus a. Now, the pink graph 4. Also, the graph for the simple harmonic motion having the amplitude is A, but initial phase is minus pi by 4. So how this particle performs the simple harmonic motion on a linear path? So again, the displacement is same, that means the amplitude is same. There is the mean position x is equal to 0. But here, at time t is equal to 0, this particle of graph 4 is not at the extreme point, but till no reaches at the extreme point. That is at this point. Therefore, its graph is started from like this. So it attains the maximum, or it reaches at the extreme point after the t by 4 time. T by 4. T by 8 time. Not t by 4, t by 8. That means the phase is minus pi by 4. So there is the concept of initial phase. Right? And this concept is very useful in 12th standard in AC circuit to represent the voltage and current graph versus time, and which current or the which voltage is leading or the lagging to each other. Here the graph 4 is lagging behind the graph 3, because the graph 3 reaches at extreme point at t is equal to 0 time, while the graph 4 reaches at extreme point 8 after the t by 8 time. T by 8 time. Okay. Now next is the periodic time. Already we discussed about the periodic time. The time required to complete the one rotation or the one evolution or the one oscillation is known as the periodic time t. Again, the time required to complete the one oscillation, one rotation or the one evolution is known as the periodic time capital T. Now, what is the angular frequency? Before angular frequency, what is the frequency f? Frequency f is the number of oscillations in 1 second is known as the frequency. Reciprocal of this, here the time required to complete the one oscillation is known as the periodic time. But how many oscillations are completed in unit time, that is known as the frequency. On the base of frequency, what is the angular frequency omega? The 2 pi times of the 2 pi times the frequency of an oscillator is known as angular frequency. That means if the frequency of oscillator is multiplied by 2 pi, so whatever the quantity obtained, that is the angular frequency. That is denoted by omega. Therefore, omega is equal to 2 pi f. Here, f is the frequency of oscillation and 2 pi is the multiplier. Therefore, omega is equal to 2 pi into f. But we know that the frequency and periodic time is reciprocal to each other. Reciprocal to each other. Therefore, t is equal to 1 upon f, or the f is equal to 1 upon t. Here we substitute. Therefore, omega is equal to 2 pi upon t. Now, we are interested to obtain this equation. Omega is equal to 2 pi upon t. That means after the one rotation, what is the angular frequency? Okay. For that purpose, we consider the displacement of a simple harmonic motion with amplitude A and initial phase phi is equal to 0 at time t is given by the equation xt is equal to either a sine omega t plus phi, phi is equal to 0, or a cos omega t plus phi. Here we consider the phi as 0. Because our earlier discussion is that we can represent the displacement by either the sine function or the cosine function. As we consider the any function, that is remains same. For that purpose, here we consider the cosine function, and periodic time of rotation is t. Again, the displacement of simple harmonic motion with amplitude a and initial phase phi is 0 at time t is given by the equation xt is equal to a cos omega t, and periodic time of rotation is capital T. So after the one rotation, the displacement is even same, because here the particle execute a simple harmonic motion. At time t is equal to 0, the particle here, it starts its motion, reaches extreme point, again return back. At that time the time is t. That means at initial time t and after t plus capital T time, the position of the particle is same. Therefore, we can write xt is equal to x small t plus capital T. Again, here the position of the particle after the one rotation is same. That means after periodic time t is same. Therefore, a cos omega t xt is equal to a cos omega t. And here we substitute t as t plus capital T time. Therefore, a cos omega into bracket t plus t. Here a cos omega is cancelled. Right? Therefore, omega t is equal to omega t plus capital T. Okay. Now, cosine function is the periodic function with period 2 pi. Because the cosine function is this shape, already we discussed. So it completes the one oscillation here. So at that time there is the 2 pi area, but the periodic time is 2 pi area. Therefore, the phase is increased by 2 pi radian after completion of the one rotation. Therefore, the phase is omega t plus 2 pi is equal to omega t plus capital T. So, omega t plus 2 pi is equal to omega t plus omega into capital T. This omega t cancel. Therefore, 2 pi is equal to omega t. Therefore, t or the omega is equal to 2 pi upon t. But we know that t is equal to 1 upon f. Therefore, 1 upon t is equal to f. Therefore, omega is equal to 2 pi f, or omega is equal to 2 pi upon t. Now, friends, here keep in mind that at given time t and after t plus capital T time, the position are same. Therefore, I have written the xt is equal to xt plus capital T. And according to this equation, I substitute the value for xt a cos omega t. Now, instead of the t plus delta t, the t plus capital T. So here a cos omega into bracket t plus capital T. Right? Now, cosine function is periodic with period 2 pi. Means the phase is increased by 2 pi radian after the one revolution or the one rotation. Therefore, we can write the omega t plus 2 pi is equal to omega into bracket t plus t. Now, omega t plus 2 pi is equal to omega small t plus omega capital T. Omega t cancel. Therefore, 2 pi is equal to omega into t. Therefore, omega is equal to 2 pi upon t. T is equal to 1 upon f. Therefore, 1 upon t is equal to f. Therefore, omega is equal to 2 pi f. That is our definition of angular frequency. Already we defined the angular frequency as 2 pi times of the frequency of oscillation is known as angular frequency. Thus, friends, we discussed about the phase constant and phase of a simple harmonic motion, and also the periodic time and angular frequency. These are the constants of simple harmonic motion. Frequently we have to find out this constant in our chapter oscillation. Here is, so there is the concept of this.